approach methodology, then presenting case studies on PV and PV systems and wind turbine systems, and then I will be proceeding to conclude. So I will start with the motivation of this work. It was under the goal, the net zero goal of carbon emissions by 2050. And that goal needs us to act fast in order to be producing more electricity from clean sources, especially as we are today producing 8% of global electricity generation from wind and 7% from solar. But the goal by 2050 is to be producing 70% of this generation from wind and solar power. And by the end, now we are 50% short from this goal. And as this demand increases, we are under this challenge, is that we have to maintain and have reliable operation in those systems. This high demand is achieved by maintenance, especially efficient maintenance. The current state in PV plants and wind farms is that we are gathering data. We have well-monitored systems. In PV plants and wind plants, we have SCADA data. Also, we can find from operators alarm and fault logs. In PV plants, we have, in some cases, IV curves at the panel level, at the array level. And we have, in some cases, in wind systems, we have vibrations of different motors. We have different data. We have also, in some cases, drone imagery. But mainly, in those plants, what we have abundantly is SCADA data. So we have data coming from different components of the system, from the PV arrays, temperatures, meteorological data, from the weather, wind speed, and so on. So, but this knowledge, this available data, does not directly connect us into health state knowledge. We don't have a deep knowledge of the health of the system. In order to answer to that, to address that, under the engineering field of PHM, prognostics and health management, we start from this acquired data from the system, and we proceed in different steps, from data preprocessing, data acquisition, data preprocessing, and then we go to fault detection in order to see what's going on, fault diagnosis to see the source, the root cause of this issues that we are facing, and then we might arrive at the end to prognosis, where we can also predict what will happen in the future, leading to decision-making in condition-based maintenance, CBM, and predictive maintenance. Mainly our work will be under the CBM paradigm, the condition-based maintenance, which will be that we, based on the knowledge that we have from the system, we can take actions. We will be focusing also, as the title of this thesis presents, it's on fault detection and diagnosis, FDD. The acronym will be, as the abbreviation will be as compound, which goes mostly in two directions. We have model-based approaches, where we could see observers, Kalman filter, for example, parameter estimation, and bond graphs, as the work of Dr. Nizar earlier. This is a pathway that we could take. And the other one, considering the abundancy of the data that we are having today, is by the data-driven approaches, such as classical machine learning algorithms, or more recently, deep learning. Both aim at increasing and improving the reliability, safety, and availability of such systems. To compare between data-driven approaches and model-based approaches, we can see here, with model-based, we need more physical knowledge with governing equations of the system, where we face that with the increasing of complexity of such systems, we have an increase in computational cost. We should go out of our assumptions that we are treating a linear system to actually be able to treat a nonlinear system, the nonlinearity in system. Other than that, we can go the data-driven way, considering the abundance of data, as I suggested, and we can, the large amount of data, we have faster computational time, and we have, with the increase of complexity, we have increase in data, and we can increase our knowledge of the system using this data, and which also in data-driven we can handle nonlinearity better than in model. Thus, we will proceed with the data-driven direction. Considering data-driven direction, we should be focusing on the word data, where it governs and it controls how we will proceed further. In data regimes, we will have two parts, where we could have annotated data, which is actually complex and expensive on operators, but we could have labeled data in systems in some cases, with fault classes, where we could have a system know which data are related to what fault that's happening, like an inverter fault in PV, a higher temperature on a gearbox in a wind plant, and so on. So connected directly with faults that we can actually analyze. In this direction, we can go with the supervised FTD, where we are doing classification and prediction based on labeled data and known faults. While in the other way, we will face, which we would face more with real data, is that we can have unlabeled or weakly labeled data, where mostly we could know in general is that when we could use much of data connected to when is the system operating in a normal way, rather than actually knowing when the faults are occurring. And this is actually what we find more in real systems. And this way, we would require a normal operation model, knowing the normal operation mode as best as possible. Thus, in this direction, we will proceed with unsupervised learning algorithms from machine learning. The thesis positioning here will be with labeled data for supervised FTD and labeled motivate, while the weakly label motivates the unsupervised. Here we can see our thesis within unsupervised and supervised. Our thesis is in the middle, as it will go in a hybrid direction and addressing when we have labels to supervised and we don't have labels to unsupervised. And between model-based and data-driven, it lies here. The contribution one that we will be speaking about is performance-driven feature engineering, which is a very main step within FTD. And contribution two would be how we will treat and extract the normal operation mode with temporal context, having much more knowledge of how the time series and the variables are evolving with time within a system. The research questions, first we will be addressing one, how can dimensionality reduction, reducing the dimensionality of with respect to the variables governing a given system, how will it improve supervised FTD without degrading diagnostic performance? Question number two, how can the accuracy complexity trade-off be made explicit and operationally interpretable? This contributes or connects to contribution one. While on the other hand, how can anomalies be detected when reliable fault labels are unavailable? And how can normal operation modeling and reconstruction error thresholding support reliable anomaly detection and real SCADA data? We will investigate that further. Now I will speak about fault detection and diagnosis in systems. Here we can see the flowchart of fault detection, FDD, starting from the data sources, the different types of components and the variables that we can have, and data acquisition, which will also pose other challenges with noise and missing values and so on. And then we go to data preprocessing, as we could consider windowing, taking the data in sliding windows, or we could, or we should actually in deep learning and so on, to be scaling the data, how we could be scaling the data in order to have a governing scale for all the variables. Then we reach to feature engineering, which connects to the contribution one that we were speaking about. How can we do a reliable feature engineering having a good diagnostic performance? Because feature engineering leads to dimensionality reduction and leads to both ways. We will be proceeding first in this direction, leading to supervised classifiers. How can we focus on dimensionality reduction, leading to a good classification in supervised map? We will speak about some types of feature selection and feature extraction methods. Here, the state of the art is that when we are treating such systems, we have high dimensional measurements, correlated variables, redundant variables, and some irrelevant variables that we don't need. And how can we choose what is suitable to our system? We do that with feature engineering. For example, with filter methods, where we have a scoring algorithm that we could use for the variables connected to the classes, such as information gain, Pearson correlation, T-square, leading to a classifier, and based on the ranking of this list of variables using these different algorithms in order to rank the variables, to select a subset and use it for training and testing for classification. The other way around is called the wrapper method, where we test with different, we don't have a scoring algorithm, we test with different subsets, use them with the classifier, train the classifier on them, and see how the classifiers are performing. And based on this performance, we iterate. If we are getting a good result, we can proceed to select this feature subset, or otherwise we will go to no. We will further investigate to get to the best feature subset. The goal is to have compact input that preserves the diagnostic information coming from the beginning. For example, here we can see this is an example of ranking different features from feature 0 to feature 7. We see how we are having different scores, but there is an open issue here in research, is that existing studies optimize feature ranking with different algorithms and so on. We see the best, which can be doing the best feature ranking, contributing to the classification, but they don't focus on the threshold itself. As I will say next, is that with low threshold redundancy, a low threshold, like a low threshold that we could have here, we will have redundancy remains. While with a higher threshold, we will be losing information. So we are playing between those two levels. So selecting an optimal threshold is an essential step in this paradigm. And then we proceed to when labels are not available. So feature selection and methods that we were speaking about, we don't have classes, so we don't have a concrete truth that we can rely on to do classification and test the performance. We go to unsupervised with weakly labeled data. The main data that we could have to have some idea of a system, as I said, is in the normal operation. We treat that as a one-class paradigm. You can see here, let's say that the blue dots are what we consider normal in the system, while the orange dots are the outliers, the anomalies. So if we train a model that knows very well the normal operation mode, so then when we face something with deviation, something odd, something new, we can detect that as it is an anomaly. And that's the analogy and the assumption and the thought that we will be proceeding with. So we will be training on normal operation behavior and use the deviation scores for alarms. But here, there is an issue that raises, is that, for example, if you are monitoring a system for 1 year, during this 1 year, we will face faults. It's possible. But then we have to train on the normal operation mode of this sequence. And we want to use as much as possible from the normal operation mode in order to train the model as much as possible on a given class, which is the main class. What raises here is that when we face faults and we are treating a time series, we have to keep this sequentiality from 1 to 2 to 10 to 100 and 1000, while we will have gaps due to faults. So how we will address that? So we are facing a fragmented normal operation mode, a fragmented NOM, and how we can address that. This is an open issue in literature, which we will address in this. So we are addressing two gaps. In supervised FDD gap, feature scores rank variables, but the threshold controls the final subset and the accuracy complexity trade-off. While in the other way, so the first gap will be performance-based feature filtering. The other way would be using real SCADA. Data can contain sparse labels and fragmented normal operation periods. How can we have a reliable normal behavior modeling? And these gaps define the methodological direction of the thesis, which we will discuss next. Starting from the supervised approach methodology, we will be speaking of a wrapper-inspired hybrid feature engineering strategy. Wrapper, where it will be focused on the performance to select the best threshold for feature ranking. And it is a hybrid method as it has feature selection as in different feature filtering methods, which we will choose one of. And the hybrid part would be to join it with a feature extraction method called different methods, but we will be focusing on PCA, which I will discuss later. This is the hybrid part, and the wrapper to be basing the performance to select the best. The literature objective, how can we improve supervised FTD by reducing redundant and weakly informative features while preserving diagnostic information, as we said already. And the methodological gap is how we can select the threshold for the filtering method to select the best subset. And we propose a method called Data Dimensionality Reduction Strategy, DDRS, where we start with the original data set, and then we do training and testing splitting, 70-30% as usual, where we have a testing data set and training data set. After scaling on the training data set, we reach ranking the features based on their information gain score. And this will be a main topic which we will discuss, is that we selected feature selection method, feature filtering method called information gain. But that is possible that we could also test DDRS on different feature filtering, but we have proceeded with IG, information gain, as it is interpretable and it's straightforward method that we can apply. And then we proceed to PCA, where we use 90% of the original information. So with IG, we will have different subsets at different thresholds, proceeding to PCA, then proceeding to classifiers using cross-validation training in order to get performance metrics. Based on those performance metrics, we will make a comparison between the different thresholds in order to select an optimal threshold which we can proceed with. This is DDRS. The role in DDRS of information gain is that it will be ranking the features. And here we see the mathematical definition of IG relying on the Shannon entropy equation. Furthermore, we get the entropy of the parent nodes and the child nodes, parent nodes and the child nodes. And we will see that in the next slide how we can calculate. So we proceed from original features, IG scoring, feature ranking, then selecting the subset. I'll give here an example of how we use IG. As we here have a group of data, actually differentiated in color, we see that. So we have blue balls and orange balls. And then we select a feature, a given feature, arbitrary feature, and we do classification based on that. So we will get two classifications on a child node, B and C. To calculate entropy in the first set, it is calculated as following, as we have the probability of the orange balls over the total number of balls, the second log, and then we continue, minus the probability of the blue balls over the total number of balls, getting the value of 0.999, almost a 1. What does that mean? Is that in this set, actually we have a very bad classification, as we almost have the same number of blue balls as the orange balls. So a 1 would tell us that there's a high entropy here, and we don't have a good classification. And then after we did this classification based on this feature that we selected, we still have 13 orange balls and 8 blue balls, getting a 0.95 and then 0.94. The weighted entropy of this classification was 0.95, and then information gain is the entropy of the parent node minus the weighted entropy of the split, getting a 0.048. It's a very low number, telling us that if we select this type of this feature in order to do classification, we get a very bad result, which is close to minimal value. This is how we can interpret information gain, and this is why we are interested in this method. Furthermore, in DDRS, we will have feature extraction. After we do feature ranking and feature selection with the filtering method IG, then we go to projecting the sub feature set into a new feature space, which is the principal component space, which relies on the explained variance value, which relies on, from the original matrix, we are getting the eigenvectors. Based on the eigenvalues, we get how much each new principal component has retained information from the original data set, and then we select the number of principal components at a retained information, cumulative explained variance information, 90%. And that's how we will be proceeding. We tested DDRS on a benchmark data set called steel plates faults. It's a simple data set, abundant in literature, which we could be using in order to validate this method. It has 1,941 samples with 27 numerical features and 7 faults. Here we can see, after applying information gain on the 27 features, how they are ranked. And then we pose the question, what is the threshold that we should be selecting in order to select the optimal sub feature set? Using DDRS and getting the cross-validation training accuracy with the different classifiers that we're testing, such as random forest and KNN and CART, we see here that we have an optimal location at 0.61, where we have the best trade-off between complexity and performance, where we reach, out of 27 features, we are starting with, to 14, and then after PCA, actually at the optimal threshold, which has the best accuracy complexity trade-off, we get to 4 principal components. So from starting from 27 features, we get to 4 principal components, passing through 15 feature subset using information gain, and we get the following result. With random forest, we have 78% accuracy, which when compared with literature, the best value that we have here in the reference is around 82%, which uses the full feature set, the original feature set, the 27 numerical features. So here we are having a good performance with the trade-off with complexity, with 4 features only. Next, after validating the DRS with the steel plates benchmark, I'll proceed to the unsupervised approach methodology. Here, we go back to the gap of how can we handle fragmented NOM. So unsupervised anomaly detection usually assume a clean normal operation mode for training. The problem in SCADA data that failure log splits the NOM as we agreed. And then here we can see how the sequence is split with fault 1 and fault 2. And now we have 3 sequences of normal operation mode. This should be 3. So with this fragmented NOM, what we propose is adding temporal features, which rather than relying on the model to have an implicit understanding of the temporal information of the time series, rather than that, because it will be splitted, we do a feature construction, we add feature temporal features, giving information of the year, the month, the day of the week, and hour. As so, now the model, when we are training the model, we have an explicit understanding of how the sequence is evolving, and thus we can concatenate the different NOM sequences. So from concatenated NOM with time context, then we can proceed to sliding windowing of the SCADA dataset, reaching to NOM model. So we preserve the non-temporal information despite fragmented NOM. But then we are facing which model to be choosing in order to do the classification and prediction. Taking into consideration that we want to do a reconstruction of the normal operation mode, and we will say why soon. So from fragmented NOM, we add temporal features, we do windowing of the multivariate time series, MTS, and then we have to have an unsupervised FTD method. From literature, we could have used isolation for it, but it can't do reconstruction, where we are assuming that we should have the original data set reconstructed, where we will have the normal operation mode. And based on this deep knowledge of normal operation mode, when we reconstruct it, we can detect the anomalies as I discussed or mentioned earlier in the one class paradigm, classification paradigm. We could have used one class SVM, but its limitation is kernel sensitive. We could have used PCA, but it is linear only. Kernel PCA has high complexity, but can handle nonlinearity reconstruction. But we chose the deep learning autoencoder, which can do nonlinear reconstruction. And mainly, it can be extendable to sequential data, where there is a lot of variance from the vanilla autoencoder, which is the basic autoencoder. We could have different architectures of the neurons, which I will discuss next, in order to handle this temporal dependency and to handle these sequences. So we proceed with the autoencoder. Then we have to select which architecture. Here in the autoencoder figure, we can see if you are starting with this multivariate time series, different variables. The idea of the autoencoder is to do a dimensionality reduction leading to a latent space, which is a compressed representation of the original data set. So let's say we are starting with 10 neurons, we lead to 2 neurons. And then we reconstruct with the decoder all the original multivariate data set, the time series, only using the compressed representation, leading to the reconstructed multivariate time series, which is WT hat, starting from the original, which is the WT. And we train the model on the concept is that we have to reach to a near perfect representation of the original data set, relying on the reconstruction error. So we are constructing every window and then getting the mean squared error in order to iterate in the autoencoder to get the best reconstruction performance. And this leads us is that when we are training on the normal operation mode, the analogy is that we will have a low reconstruction error. And then when we are facing real data, new online data, if we are addressing a normal operation mode, we are receiving normal operation mode, we will have a low reconstruction error. While if we face an anomaly, something deviating from normal operation mode, we will have a higher reconstruction error, thus detecting a fault. The different architectures that we could be using, we can see here, there is the fully connected NN, a neural network, as in the vanilla autoencoder, or the convolution neural networks, which are more compatible with image processing, or the recurrent neural networks, such as long short-term memory cells, or the bidirectional long short-term memory. We select that we have to focus on the RNN variants as it handles sequential data better than the others. But then we are facing either choosing BiLSTM or LSTM. Here we see the gates of the LSTM model, which regulate what information is retained, and then we update and predict at each timestamp. But we use the forward pass, using the past in order to predict the present and the future timestamps. While in the BiLSTM, we have forward pass and backward pass. So if we are in a window, we are using for example, the next window and within the window, we are using the next timestamps and the previous timestamps from 1 hour, for example, in order to predict at this window, is it faulty, is it anomalous, or not? We proceeded with the BiLSTM As it learns long-term dependencies relevant to wind turbine and PV plants, and uses past and future context during training, and it is convenient for normal operation mode model. Here we have the mathematical notation that we will be using, where we are starting with the matrix, the original multivariate matrix at each time step, and then we do windowing using tau as a window size, and then we get the new matrix of the different windows, proceeding that we have to get the anomaly score at each window using the MSE in order to select if we are above epsilon, a given threshold that we will be selecting, we will be either anomalous or normal. Here, in the flowchart of the BioLSTM autoencoder, we are starting with the multivariate time series. We are extracting the normal operation mode, then adding temporal features in order to concatenate this normal operation mode, then converting this data into windows, and then we are training on the normal operation mode, as I already said. Then we select the, we do threshold selection after training of the normal operation mode, as we will get the different reconstruction errors in the training step in order to select the threshold. Based on that, we will be getting either we are above the threshold, we are an anomaly, below the threshold, we are in normal. And here there is a step of hyperparameters tuning based on how we can change the threshold in order to see how sensitive to how we can address the false alarm rates and the misdetection rates and so on in evaluation. Next, I will be speaking about the results, the case studies in PV and wind that we had, starting with solar panels data set published in 2020 by Azzuddin. Yeah. It is 8 classes, 1 normal operation mode, and 7 for different classes. It is experimental, it is simulated, and it has 15 seconds per fault with 13 features governing the system. This is the system with solar array emulator and the DSpace 1100 environment in order to get the data and to simulate the system with grid emulators and so on. As I said, it has 8 classes, 1 for normal, 7 for the others, and each class is monitored for an average of 14 seconds with a 10,000 samples rate. And we have eventually a training data set of 440,000 data points. Here we see the different features. They are mostly electrical variables from the system, electrical signals. And here we see how the data is organized. What is the data set? So we have from F0 to F7, F0 as in the normal operation mode, and then we have, for example, F1 a failure in the inverter, F3 grid voltage sag anomaly, and for example, F4 the partial shading mismatch. And then we have the different original data set, which we have to note here that the fault is induced not from T0, it is induced at some given point in the middle of the data set. So if we take the full, for example, in F1, if we take the full data set and considering as label it as F1, within this F1 data set, there is normal operation mode. So we can't do that, but we know when was the fault induced, and we take the data set after the fault is induced. So we end up with this final labeled sample data set for each class. We note here that for F3, we started the final labeled sample data set was 4,961, but we used a data augmentation method called SMOTE, synthetic. I memorized the abbreviation, but I forgot. So SMOTE, which relies on the normal distribution of the data in order to create and augment the F3 in order to have a balanced data set. Here we got the information gain scores of the different features, and we see that we have how the different features are contributing to the classification. In order to select the optimal threshold, we see from this graph that at 0.83, we have the optimal threshold tau star, where we have the best trade-off between complexity and performance. Here, we compared the result at this optimal threshold with the baseline accuracy using the full feature set, and with what we found in literature is that with information gain, they usually, in multiple papers, they use the threshold as it is the standard deviation of the different scores. And we compared our results, finding here how at T star for random forest and for the other classified, we are getting a very good result in comparison with the others. We are not saying that it is performing better, but we are, but at the same time, it is much less complex with only 3 principal components being used. And we see here in training time, for example, for random forest, at tau star, we only take 38 seconds to train the model. With CART, we are only taking 100 seconds, which is much less than the baseline, close to the tau of the standard deviation. And then we compared our results with literature, seeing how the accuracy that we are getting with DDRS with 3 principal components, 3 features, starting from 5 features after information gain and 3 principal components, the result that we are getting, which is very comparable and performing quite well in comparison with literature. Then, using this offline training of the FTD model, we proceeded to real-time FTD, where we fed the model with the 140,000 data points at each class in order to find if the model, for example here, the KNN classifier is detecting the fault in a fast manner, in the correct time. And we can see here, the dotted line is where the fault is induced. And we see here in the orange line, are we detecting the correct fault every time? And we achieved that in every case. So the research questions addressed here is research question number 1, where IG ranks the feature relevance and PCA extracts the compact components, and then the classifier evaluates and confirms that FDD performance is preserved after reduction. And the second question, RQ2, we have explicit accuracy trade-off, accuracy complexity trade-off, where we have an interpretable result, as we are seeing how the performance changes with threshold, different thresholds, in order to have an explicit knowledge of what we are doing. Then the second case study is on Energia do Portugal from Portugal. They published a data set in 2018, having recordings from 2016 and 2017 over 2 years. A data set that includes 5 turbines, 5 identical turbines, 2 megawatt each. It has multivariate time series. It has operator fault logs. It's, we can say, the real case, what we could find in a plant with 81 features. We can see here the fault logs. As you can see here with the T01, we have 2 faults recorded by the operators, having a fault in July 2016 and in August 2017, only 2 faults in T01. But you can see here is that if we have to use this information to label the data as it's supervised, we would only have 2 points of information over 2 years at this timestamp, at 2 o'clock in the morning. Only this information is there. So if we go to use supervised, we can't use this information to label a data set. What we do is that we avoid those faults in order to get the normal operation mode, which we can actually extract. Here are the selected features out of the 81, as the 81 included statistical features at minimum, for example, for the nested temperature, we have the minimum value over 10 minutes and the maximum value and the mean value. We only took the mean values at each 10 minutes interval. Here we can see, for example, not for example, actually, we selected T01 as it has the least number of faults, as it has 2, where in this case we will have the largest number of data for normal operation mode, and we used information that was shared by EDP, telling us that if we avoid 60 days before default, we can consider that we are in normal operation mode. So we avoided this interval 60 days before the failure log 1 and 60 days before failure log 2, and extracted two normal operation sequences. And then we added temporal features, as we said, and we got a new feature set for the NOM. And then after training our model on the different variables of the wind, for example, here we can compare between the T01, the total active power production in blue, and the reconstructed feature. So here we reconstructed the variable in a near perfect situation. Then we got the reconstruction errors, where we did KD estimation to get the cumulative distribution function, where we selected the threshold at 99%, 99.95% for the normal operation mode, saying that we trained on normal operation mode. We selected this threshold, as all of the reconstruction errors that we are getting in the normal operation mode training should be telling us that we are normal. So we say that above this threshold, we are in an anomaly, are detecting anomaly. Here for the first fault, before August 18, we can see how we are detecting the fault just near that time and within the 60 days period. And when we are detecting within the 60 days period, we consider that we detected a true positive. We detected correct. And for the second fault, we also detected within the 60 days before the fault is occurring. And then here for the full sequence, we detected when we then tested it and validated on the full sequence, not only on the fault the 60 days before fault 1, 60 days before fault 2, where we detected the fault within the time before the faults occurred. And we only got out of 80,000 data points, we get only 325 alarms, out of which, for sure, there's false positives. But we were detecting, in most of the case, within the interval of the faults occurred. Then we tested this without training on other turbines. We only trained it on the normal operation mode of turbine 1, and then we tested it on turbine 7 and 9 and 11, and we will see here in 9, where we are detecting, we have 5 faults, and we can see how we are detecting the faults also in the time where the faults are occurring. For example, here in January of 2017, we can see here that in January of 2017 we have a generator bearing, and the generator bearing was replaced. And we see here how the reconstruction error increased massively above the threshold in green. Out of 80,000, total triggers were 1,232, and we had 199 false positives out of the 60 days period. Thus, the precision was 83.85, with a false alarm rate much less than 1. Then we have the results with the different turbines, where we note that we were not detect in T11 the faults, but we were able to get a good precision in 6 and 7 and 9. While in 1, which is actually the turbine that we trained on, we only got 320 triggers, but we got false positives out of the 60 days period, where we got a low precision. But we were able to detect the faults. Noting here that those false alarms, we are not saying that we have to be telling an operator that there is 100% there is an error. It's an alarm for them to go check and to be able to monitor the system. So this method answers the research question 3. The model is trained only on extracted NOM data and detects deviation using reconstruction error without requiring class labels. And the research question 4, the NOM modeling and threshold-based detection, BioLSTM addressed that with temporal features and sliding windows that preserve data context. So starting from NOM extraction, going to temporal features, and then anomaly score thresholding in order to get anomaly detection. The limitations of this work, with the supervised DDRS, is that we validated this on a labeled data set, but it's an experimental data set. And the second is that we depended that those are reliable fault class data. Then with the unsupervised, we were able to achieve only fault detection, no diagnosis or component localization, and the threshold was fixed using the reconstruction error. And we had point estimate alarms rather than considering uncertainty. Those were the limitations of this work. And industry data constraint is that the failure logs can be delayed or imprecise. And the NOM extraction depends on operator information, as in the 60 days information that we got from EDP. Those were the limitations of this work. So the thesis demonstrates reliable detection and dimensionality reduction, but the complete PHM chain also is missing, as we did not reach prognosis, and where PHM still requires fault localization and fault diagnosis. Then proceeding to conclusion, where contribution 1 with the supervised FDD and DDRS, information gain was used to rank the feature relevance. PCA extracted compact diagnosis components, and the classifier performance selected the feature threshold. Contribution 2 with the unsupervised anomaly detection, and NOM is extracted from weakly labeled failure log information, only to extract the NOM. The temporal features were added to handle fragmented NOM periods. The bi-LSTM autoencoder detected deviations through reconstruction error. The overall contribution of this work, the work connects feature engineering-based supervised diagnosis with reconstruction-based unsupervised monitoring, supporting PHM-oriented decision-making for PV and wind energy systems. The perspective is to be testing, for example, DDRS on real dataset of PV, but it should be on a panel level and could be investigated also on the inverter level, which is actually the case that we could face more in PV plants. For fault diagnosis, we should move with bi-LSTM autoencoder beyond detection. We tested actually our work with contribution plots, where we could connect the reconstruction error of every variable that is reconstructed. That's not working. Reconstructed. And then, for example, if we are getting a high temperature for the bearing oil, so we can connect that we are having a higher reconstruction error due to this temperature in the oil bearing, where we can connect it to a fault in the bearing. So we were investigating that, but we did not get to a good result. It's still in the perspectives of this work. And then for uncertainty, for the autoencoder, there is an option where we can use Bayesian deep learning, such as variational autoencoder, where we can take into consideration uncertainty with each prediction, opening this door for having more realistic estimation at each point. And then the PHM extension with fault prognosis and RUL estimation. This work was valorized in a Q1 journal in 2023 with DDRS. This paper was cited already, I think, above 40 times. And then it was also orally shared in conferences. The second contribution with the bi-LSTM autoencoder and the temporal features generation was published in a conference paper, IEEE conference paper in 2024 in the United States, which they gave me actually. I will tell a story. So for this conference, I was applying to go to the United States. It was in June. So I was accepted in March. So they gave me an interview date. As I'm Lebanese, I don't have the right to go directly. So they gave me, it was in 2024. They gave me a date in September 2025 for an interview to attend a conference in 2024. So I attended online, but it's already cited 10 times, and it was valorized. In the end, I present this with deep gratitude to my late father, which died in 2007, and to my wife here, and my friends, all my friends, and all my colleagues, with deep gratitude. And then I consider this work in memory of friends that I lost during the war in Lebanon, during the past 3 months, 3 paramedics, Ahmed Hariri, Fadl Sarhan, and Muhammad Muaddim. Those were very close friends of mine that were doing their paramedic job, helping civilians and taking them from under bombarding and tedious reality. So I acknowledge them and with deep breath. And that's it. Thank you very much. Questions and answers.
Okay. So thank you very much. Mr. Bassel Shukr, thank you for your presentation. I find it really interesting and very, very didactic, and it summarizes your main contribution. And maybe I will not take more time, and we'll give the floor to the Q&A session. And we'll start first by